Hello, hello, hello. In this worked example, we're going to talk about free body diagrams, a very useful tool when you work on problems involving Newton's second law. So let's dig in. So the second law, as you now well know, tells us that we can calculate the acceleration of some body or object in terms of the net force that acts on the object and the mass of the object. So, a essential part of solving problems involving Newton's second law is to be able to calculate the net force that acts on the body, the object in question. And the free body diagram is sort of a tool, a little device that we use to help really systematically identify the forces that act on the object that contribute to this net force. So let's see how it works. So we'll take a simple case at which the body is, say, your body, and you're standing at rest on the in your room, say, and we want to, if you're at rest, we know that your acceleration of your body is zero. So the second law, this is the second law, the second law implies, therefore, that the net force on your body is zero. And the free body diagram is, as I said, a way of identifying the individual forces that contribute to this net force. So the way the free body diagram works is we're going to represent your body, whatever the object is in question, by a dot, and then we're going to draw arrows whose tails are connected to the dot that are associated with the individual forces that act on the body. So if you say, uh, in this particular situation, what are the forces? Well, there's of course the force of gravity, and that acts in the downward direction. So we'll draw an arrow that looks like this. And this is the force of gravity that acts on the body. And then what other forces are there in the problem? Well, there's only one additional force of consequence, and that's the so-called contact force that is exerted by the ground on your body. And that is, of course, an upward going force. So I'll draw an upward going arrow, and we can call this the force of the ground. And it's implicit in both of these cases that these forces act on you because you are the body. So that's, and notice that I drew these two arrows to be the same length because the net force is going to be the sum of these two forces. And we know that the net force has got to add to zero. So these two arrows have got to be of the same length. And this example sort of illustrates that there are really two types of forces that we're going to encounter in this course. And each of those two types is represented in this problem. There's a so-called contact force, which, as the name suggests, uh, is associated with something that's actually touching in contact with the body. So in this problem, the force that the ground exerts on you is a contact force. Is an example of a contact force. And for the most part, the forces that we're going to encounter are going to be predominantly contact forces in this course. The one exception is a force like the force of gravity. And the force of gravity we sometimes refer to as an action at a distance force. So the way gravity works is it doesn't have to be touching you in order for the force to be exerted. The law of gravity says that two objects, no matter how far apart they are, the gravitational force exists between them. So, as a device, when you go to draw these free body diagrams, the first thing you should do is look at, once you've identified the body, you want to say, what is it that's actually touching the body? And those will lead you to all the contact forces in the problem. And then you always have to, in addition, say, well, is there gravity in the problem? That's an additional force that you'll need to add. So that's a very simple example of how a free body diagram works. Let's take a slightly more complicated problem. So here's the problem. There are two identical blocks, and they're connected by a spring. And the whole thing is at rest because connected to the upper block is a string, and that string is connected to the ceiling. So the whole thing is just hanging stationary. And we'll we'll label this we'll call the upper block, and this is the lower block. And now we're asked to draw free body diagrams for each of these two blocks. Okay, so let's do it. So we'll start with the lower block. So I'll draw a little dot down here to represent the lower block. And what are the forces that act on the lower block? Well, following the guidance that we just gave, we're going to first look for contact forces. What is it that's actually touching the lower block? And obviously, there's only one thing touching the lower block, and that is the spring. So the spring is going to exert a force on the lower block. And the spring is a stretch spring. So if you think about it, if you say stretch a rubber band in your hand and feel which way the forces are exerted, it's pretty obvious that this stretch spring is going to exert an upward force on the lower block. So we'll call this F spring, comma lower. That's the force of the spring on the lower block. And that's the only contact force. And then there's, of course, the force of gravity that acts on the lower block. And that is obviously a downward going force. And because the lower block is at rest and not accelerating, we know that the net force on the block has got to add to zero. And these are the only two forces that act on the lower block. So it's pretty obvious that the length of these two arrows that appear in our free body diagram have got to be the same in order to get a net force adding to zero. Okay, let's move on to the upper block. The upper block will represent by a dot up here. And let's identify the forces that act on the upper block. Let's start with the contact forces. So now we want to look at the upper block and see what is actually touching the upper block. And well, there are really two things. There's a spring and a string, and those are each going to exert forces. Now, the spring, the stretch spring, the force that it exerts on the upper block is going to point in the downward direction. And so there's a force F spring, comma, upper. Force of the spring on the upper block. And notice that I've drawn the length of this arrow to be the same as the length of this arrow. And that's really a property of springs. When you stretch them, the forces that they exert on either end are point in opposite directions, but have the same magnitude. That's a property of springs. So that's one force. And there's an additional contact force due to the string that is exerted on the upper block. And the string force clearly is going to point in the upward direction. So there's a force on the upper block of the string, and I'm going to call that F sub string, comma, upper. So those are the two contact forces, and then in addition, there is a downward force of gravity that acts on the upper block. So that's the force of gravity sub upper. Now, a couple of things to notice. One is we're told in the problem that the blocks are identical, which presumably means that they have the same mass. So that means that the length of these gravitational forces here, these arrows have got to be the same length because the masses are the same, and therefore the force of gravity on each of the blocks is the same, both magnitude and direction. And you notice that I've drawn the length of this arrow to be the same as the length of this arrow. And if you follow through our logic, you'll see why that is. We've argued that this arrow is the same length as this arrow, and that this arrow must be the same length of this arrow because of the way springs work. So therefore, it follows that these two arrows have the same length. Okay, and that means the last thing we can say is because we know that the upper block is at rest and we've identified now all of the forces that act on the upper block, and since we know that these forces have got to sum to zero because the upper block is not accelerating, that must mean that the string force that is exerted on the upper block actually has got to cancel these two forces. So that means the length of this arrow really needs to be twice the length of these arrows. So let me clean this up a little bit. I'm going to make my upper arrow a little bit longer so that it looks like it's twice the length of these two arrows. So that's it. We've successfully answered the problem. We have drawn free body diagrams for both the lower and the upper blocks. And in each case, the arrows that we've identified in the free body diagrams, if you sum those vectors together, you get zero because we know that the blocks are not accelerating. Okay, one last question. Suppose the spring breaks. What happens in that case? And in particular, what is the downward acceleration of the upper block? So what we're imagining is this is a situation that we had from the previous slide before we cut the string, and what's going to happen to the upper block right when we cut the string. Well, when we cut the string, what we're doing is we're getting rid of this force here. But at the instant that you do that, the spring is going to be uh, stretched the same amount that it was right before you cut the string. So the spring force is going to be unchanged, at least for a moment, and the gravitational forces are going to be unchanged. So if we look at our free body diagram now for the upper block, we can see now there are only two forces acting on it. They both point in the downward direction, and that's going to cause the downward acceleration of this upper block. And what is that downward acceleration going to be? Well, surprisingly, we can answer that exactly because there are two forces that act on the upper block. The gravitational force, if that were the only force that acted, we know that the acceleration would have a magnitude 9.8 meters per second squared. But now we see that the spring is also exerting a force of the same magnitude in the same direction. So that's going to double the acceleration. So instead of accelerating downward at 9.8 meters per second squared, the upper block is going to accelerate downward at 2 times 9.8 meters per second squared. And if I'm doing my addition properly, that is 19.6 meters per second squared. So the acceleration of the upper block right after the spring is cut is equal to 2 times the acceleration due to gravity, which is got a magnitude of 19.6 meters per second squared, and the direction is downward. So that is our answer. And that's it for this worked example. Hope to see you again soon. Bye-bye.